So super quick summary of our last video. We created a vector and we found a orthonormal basis other than the standard IJK basis. We actually found how to write that vector as a linear combination of our non-standard orthonormal basis. And we even found the length of that vector and found out that it was the same length as the original because we just had two different orthonormal bases. Now let's try something else pretty cool. Let's take our A vector that we made up. In my case, it was -2, 4, 3. I'm going to rewrite that down here. And we're going to inner product him with each of the V1, V2, and V3 vectors and see what happens. So if I do the inner product of A with V, I've got the vector -2, 4, 3, inner product with 4/5, 3/5, 0. Okay, and unless I tell you otherwise, use the standard Euclidean inner product. So we'll get -8/5 plus 12/5 plus 0, which happens to be 4/5. Okay. How about A inner product V2? So we'll have -2, 4, 3 inner product with the vector -3/5, 4/5, 0. We'll get 6/5 plus 16/5 plus 0, which makes 22/5. And finally, A inner product with V3. So we've got -2, 4, and 3 inner product with 0, 0, 1. And we'll see that that's 0 plus 0 plus 3, which is 3. And do you notice something pretty cool? These guys are actually the corresponding coordinates of our vector with respect to the non-standard orthonormal basis. That's pretty cool. And W/R/T is a common shorthand for with respect to the S basis. Cool. All right. Now, if we're lucky, we start off with an orthonormal set of vectors, but sometimes we're not so lucky and we need to make an orthonormal set, an orthonormal basis. And that's what we call the Gram-Schmidt process. So we're going to first orthogonalize the vectors and then normalize the vectors. Now you can normalize the vectors as you go along, and remember that in this case what we mean normalize is length 1. Okay, and there's pros and cons to each way of doing it, but where we're first learning this, I'm going to recommend that you first orthogonalize all the vectors and then go back and normalize all the vectors. Okay, it will involve fewer square roots if you do it that way by hand. So let's take our vectors. U1 is 2, 1, 0, U2 is -1, 1, 0, and U3 is 1, 1, 1. You can note that these guys are in fact linearly independent. Okay. But you'll notice that these guys are not length 1. This is length square root of 3, length square root of 2, and length square root of 5. So they're obviously not 1. So now let's jump back to chapter 3 when we first learned about the orthogonal projection. So if I take some vector A and I want to orthogonally project him onto some other vector B, okay, the way we did that, or the way we kind of thought about this, is if we project our light orthogonally onto B, it's going to cast a shadow. And let me call this vector here, I'll call this vector C, and I'll call this vector that's left over from the shadow up to the desired vector, I'll call him D. So we're going to, in essence, have C vector is the orthogonal projection of the A vector onto the B vector acting like the screen that we're projecting onto. Now, another thing that you want to note is that the C vector plus the D vector is equal to my original A vector that I was starting with. And with this, notice that the D vector is equal to the A vector minus the C vector. And when we do the orthogonal projection, the D vector will be orthogonal to the B vector itself here. Okay, so take note of that, and it'll be very important here in just a second. So when we take away, if I do D is the A vector minus the orthogonal projection onto the B vector, that gives me an answer that is perpendicular or orthogonal to the B vector. So let's get back to our Gram-Schmidt process. So remember that we want to orthogonalize, and then if we're doing this by hand, normalize second. So we have to have some place to start with. So we're going to let V1 be a new vector, and we're going to let that be the U1 vector, whatever he was to start with. You have to have some starting place. So we're going to start with the vector 2, 1, 0. Next, we're going to take the second vector and make him be orthogonal to the first vector. You can check right now that -2 plus 1 plus 0 is -1, which is not 0. So these are not currently orthogonal. So we want this next vector to be orthogonal to the first vector. So using what we just learned right over here, we're going to make V2 vector be orthogonal to the V1 vector by letting V2 vector be the U2 vector subtract the orthogonal projection of the U2 vector onto V1, which in essence, like we did just a minute ago, what that's going to do is going to project on here, take this projected part away, and give me a vector that's orthogonal to the thing that I projected onto. So when I take this and project it onto V1 and then subtract that from the U2 vector, this V2 vector will then now be orthogonal to the V1 vector that I chose to start with. So let's remember how to do this. So our orthogonal projection is do the inner product over the magnitude of what you're projecting onto squared times the vector you're projecting onto. Remembering that the U2 vector was -1, 1, 0, minus the inner product we just got done saying is -1. The V1 vector himself was, if we remember from just a minute ago, let me slide this back down, 2, 1, 0. So the magnitude of V1 vector squared is 2 squared plus 1 squared plus 0 squared. Technically, we need the square root, but since we've squared the magnitude, the square on the magnitude will undo that, and we'll just get 5. So we have our U2 vector minus the inner product over the magnitude of this vector squared, which was 5, times the V1 vector. And when we push through the algebra on that, we find out that the vector is -3/5, 6/5, and 0. And just as a quick review, V1 vector was 2, 1, 0. And so if we take this guy and we do an inner product of V1 with V2, let's just do a quick check to make sure that I haven't made any silly mistakes along the way. I'll get -6/5 plus 6/5 plus 0, which is 0, telling me that yes, the V2 vector is now orthogonal to the V1 vector. Now, if you want to, some people recommend normalizing as you go along. So you could turn this into a length 1 vector, but that's going to involve more square roots. And if I'm doing this by hand, I'm going to wait to do that till later. All right, so now we've got 2 orthogonal vectors. We now need our third vector to be orthogonal. Remember that our third vector was 1, 1, 1, which is certainly not orthogonal to V1 or V2. So what we need to do is use this process and take away the stuff that points in the direction of V1 and in V2 so that we end up with what is going to be perpendicular to both of those. So we take our U3 vector, take away what's in the direction of V1, take away what's also in the direction of V2, and when we do that, we'll end up with something that has to be orthogonal to both of V1 and V2. So V3 vector is going to be U3 minus the inner product of U3 with V2 over magnitude of V2 squared times vector V2 minus U3 inner product V1 over V1 squared times V1. So remember to make sure that you take your vector and subtract his projection onto any of the other vectors that you've already made. Okay. And if you follow the algebra through here, we'll get the vector 0, 0, 1. And you'll notice that that is in fact orthogonal to V2 and to V1. So we'll pause right here and pick up in the next video.